Hello and welcome to this clip going through the level question on the Haber process. So the question gives us the equation and it also tells us what the enthalpy is for the forward reaction. And it's worth remembering whenever you get given the enthalpy change for a reversible reaction, it's always the enthalpy change for the forward reaction unless otherwise stated. So looking through the question, it says that most manufacturers run their chemical plants at temperatures between 623 and 823 K, pressure 100 to 200 atmospheres, and with the reaction vessel containing finely divided iron. So obviously the finely divided iron means that that's the catalyst. So you can see I've highlighted three things. So that allows us to plan out the question and put our answer into three subheadings. So with all level questions, it's always worth spending a minute or two doing a quick plan before you start. Now we've obviously worked out that there's a temperature section, a pressure section and a catalyst section. So the temperature is rate of reaction versus yield. In other words, the rate of reaction can be increased with higher temperature, but that won't actually increase the yield because, as you can see, the forward reaction is exothermic. I'll go into this a little bit more when I do the section on temperature. Moving on to pressure, the yield of NH3 is going to be quite high. But at the expense of the plant. So what that means is the actual industrial plant that's built to withstand such pressures is expensive and can be dangerous if there's a leak. So the catalyst is there to reduce the activation energy, which means that it works at a lower temperature, so the energy demand of the reaction can be reduced, but the equilibrium is unaffected. So it's always worth crossing through your plan if you're doing it in exam conditions, but then you can use your plan to construct your answer. So the first thing I do is I put down my three subheadings. Now what I can do is focus on each of them one at a time. So the forward reaction is exothermic at minus 92 kilojoules per mole to minus 1, so high temperatures will reduce the yield of ammonia. So you can say a reasonably high temperature will increase the reaction rate without excessively affecting the yield of ammonia. So moving on to pressure. So you need to explain that there's less moles of gas on the right hand side compared to the left hand side. So high pressure will shift the position of equilibrium to the right. So you need to say that this will increase the yield of ammonia, but also put in the fact that too much pressure will be expensive to maintain, also possibly dangerous if there's a leak of gas such as toxic ammonia, in terms of the chemical plant itself. So the presence of your catalyst will increase the rate of both forward and reverse reactions, but the equilibrium will be reached more quickly. It will also reduce the operating temperature of the reaction, giving it a lower energy demand. So to summarise, we can say that we've got a compromised set of conditions which offer an optimum balance between a good rate of reaction and a reasonable or acceptable yield of ammonia. Okay, so hopefully this clip has given you some insights on how to approach this type of question on equilibria. In the meantime, thanks for listening, and until next time, see you soon.